Okay, so clearly we got this final exam coming up, and a lot of people have been asking for a little review on acid base, and so I've decided I pretty much would take one of the more difficult problems for acid base and kind of run through it and how I rationalize it and how I think of it. So this problem is number 13 from Brian's SLA worksheet 2.4, which I've posted on the Google Doc, which is on the Facebook page if you want to look at that. So you can find this problem there and the work posted, but I'm going to run through it and how I kind of think of it. So I'm not going to read the problem. You can go through and read it for yourself, but I'm basically just going to, first, I realize I've got two different pKa values. I have pKa1 and pKa2, so I'm going to call that pKa2. So that tells me I have a diprotic acid that I can lose a proton at pH 2, and I can lose a second proton at a pH somewhere between 5 and 8. And I'm going to be trying to find pK2. So first thing I do, always with these acid-base problems, is I come up with this equation, and I always use, even though it says compound X, I like to use A, just because that's what I'm used to, and that's what I use for all of the problems. So at pKa1, I'm going to lose this first proton, making HA minus. And then this will be representing pKa2 right here. Okay, so I'm going to leave that as is right now. I recognize pKa2 is, or I'm sorry, pKa1 is 2.0. And now I'm going to find what information I have and realize what I'm doing here. So it tells me I'm adding 75 milliliters of, I don't care about the concentration right now, I'm adding 75 milliliters of a base. I got an OH there, so it's a strong base. I'm going to be adding that to some compound X. And before I've added it, it tells me the pH is 2.0. And we see that as I add it, the pH rises to 6.72. Well, I can think of that and say, okay, does it make sense that the pH is going to rise? Well, yes, it does, because if I'm adding a base, I expect the pH to rise. The opposite is true. If you are adding an acid, you expect for the pH to decrease. So I can continue with this problem, and I want to realize what's going on. So in this solution, I have compound X, but I don't like X, I always use A, so I've got A in here. But what I don't know is how much of the A I have in the most ionized form, the A2 minus. I don't know how much I have in the A minus form, and I don't know how much of the H2A I have. But that's sitting in a beaker by itself, and then I also have my base here, NaOH. Okay, so before I can start adding these things together and titrating them, I have to figure out what these concentrations look like inside the beaker beforehand. So that's what I'm going to be doing first. So it tells me I had 100 milliliters of 0.1 compound, 0.1 molar. So I want to take the information I'm given and I want to maximize it. So I have 0.1 liters, or 100 milliliters, and if I multiply that by the molarity I'm given, 0.1 moles. Molarity is always moles over liters. So I'm going to convert this to milliliters since I already have milliliters there, and I'm going to write 1,000 milliliters because I need my units to cancel. And I'm going to multiply that, and that's going to give me what is that, 0.01? Okay, and so from there, that tells me I've got my units left over, 0.01 moles of my compound A. Okay, but now still I don't know how much is in the ionized and unionized form. So now in order to figure that out, I realize the problem tells me before I've added anything, this is sitting here at a pH equal to 2.0. If you realize that pH is equal to my pKa, we know that when pH is equal to pKa, my amount of conjugate acid is equal to my conjugate base. It's 50-50. So that tells me I can split this up 50-50. If I divide the 0.01 by 2, that's going to give me 0.005 moles of the acid species and 0.005 moles of the basic species. Now you ask me, well, what about the A2 minus? Well, when your pH is equal to pKa, you have 50-50. 50% of the acid, 50% of the base, leaving 0% left for that species. So the pKa that it is, or the two species surrounding the pKa that equals your pH is going to be the two species you have in solution. Okay, so I've got that beforehand. That's what it looks like. So I know everything that's going on with this beaker before I added it. Now I got to figure out what's going on with my NaOH that I'm going to be adding. So for that, and this is for compound A, for my base, it tells me I have 75 milliliters and a molarity of 0.1 moles. Okay, and again, it's over 1,000 milliliters or 1 liter. So if I multiply that together, I'm going to get 0.0075 moles of, I'll just call it OH minus. I don't care that it's bound to an Na because it's going to completely dissociate in water into the ion forms, which OH is the only thing that's going to matter to me. So now I know everything that's going on before any addition. So I can start to pour in some of my base into my solution. But I notice 0.0075 moles of my base is greater than 0.005 moles of my H2A. If you're adding a base, the base is always going to react with the most acidic species first. So the most acidic species is going to be your H2A because it has two H's instead of just the one. So this is a better acid. So the base is going to prefer that. I used the analogy earlier today. If I like pizza and I like tacos, but I like pizza more, and I got a pizza sitting there in front of me and a taco sitting in front of me, if I like pizza more, I'm going to go for the pizza. So this OH is going to go for that pizza. It's going to bind the most acidic thing. Okay, so the base is going to react with my acid. So I had 0.005, so you can kind of separate this a little bit. So this is before addition of the two together. Everything above this is before, and now this is after. So I got 0.005 moles of the H2A, and I'm going to react that as much as I can with my base. So I can only react as much as I have. So I'll subtract that. So I'm going to use up 0.005 moles because that's going to be reacting with my base. Therefore, if you react, you subtract. So I'm going to leave me with 0 moles of H2A after I've added some base to it. Now, I have to realize I used up some of my base right here, so I have to also subtract from there. Base reacted, so you subtract. React, subtract. So now, I have what's left over. So I have 0.0025 moles of my OH left. Okay? So I haven't quite fully accounted for this reaction I did between the H2A and the OH. When the H2A and the OH bind together, they're going to form something. So beforehand, I had 0.005 moles of my HA, and now I'm forming more of my HA because as the base reacts with my acid, I'm going to have to add 0.005 moles of HA minus. Okay, so because what happens is my H2A is going to bind with this OH, and this oxygen is going to be able to take one of those. I can make water and HA minus. Okay, so you can see this is being used up, this is being used up. So that's why we subtract from both of those, and we're going this way, so we make some of this. Okay, so that's a very important concept right there. So now I've got 0.01 moles of HA. So what do I have in my solution right now? I've added in 0.005 moles of my base into my solution. So I'm actually left with some of my base left to react. I said I got 0.0025 left. So I've got to finish accounting for that. So this base is going to react with what's now my acid. So if I just bring this down here, 0.01 moles of HA minus. That's going to react with the remaining base. So react, subtract 0.0025 moles. And that's going to give me 0.0075 moles of HA minus. Okay, and then similar situation to that reaction, HA minus plus an OH. Oh, sorry if that went a little jiggly there. This is going to react to form water and A2 minus. So I'm using this, so I've subtracted. And I'm going to subtract the 0.0025 I used, and that's going to give me 0 of the NaOH left. So that's been completely accounted for. And since I've reacted those two things, HA and OH together, I've formed some of this A2 minus. So I said before I had 0 moles of A2 minus before I added any of the base. But now, because I've reacted my HA and my OH together, I've formed some of the A2 minus. And I form as much as I've used because matter cannot be created or destroyed. So 0.0025 moles of my A2 is added. All right, and so now we're going to have to convert these to molarity to put them back into the Henderson-Hasselbalch equation. Because if I remember, I'm still trying to find the pKa. So getting to pKa, I have to think, okay, what equation do I know relates the information that I'm given and the information that I'm looking for? So I'm given now concentrations of the conjugate acid and the concentrations of conjugate base. I have the pH given afterwards, 6.2, and I'm looking for pKa. So Henderson-Hasselbalch equation tells me pH is equal to the pKa plus the log of the base over the log of the acid. And those are concentrations. So you have to make sure they're in molality. So in order to get these to molality, I have to divide by the total volume now. So it tells me in the problem I originally had 75 milliliters of the base, 100 milliliters of the compound X. I've now put those in the same beaker. So my total volume is going to be 175 milliliters. So I'll divide by 0.175 liters. And that will give me a new concentration. I can do the same thing over here, 175 liters. And that will give me a concentration as well. So you can calculate this out when you get 0.143. I don't know how far you want to carry it. 0.75 divided by 1.75, and that's going to give you 0.043. Okay, so now I can plug these values into my equation. This pH I'm given is 6.72. It's equal to pKa. Oh my, I'm sorry about that. So what I did was I divided by the total amount of liters that we have now, and it gives me the molar concentration of my acid and the molar concentration of my base. So these are going to be important values. And now I'm about to plug them into the Henderson-Hasselbalch equation here too. So I'm going to use a log of concentration of my base, 0.0143 molar over 0.043 molar. And that's for A2 minus and HA because you wanted to keep it base over acid. And when I plug this in, I can solve for pKa. And I find pKa is equal to 7.2. And does that make sense? Well, it tells me that the pKa for pK2 is between 5 and 8, so that kind of checks out, and everything seems to work well. So that's one of the more difficult problems with acid-base and a diprotic acid. So if you have any questions about this, feel free to let me know, and hopefully we can help you out.